Today we're going to talk about global warming, the hows, the whys, and how we know it's us, basically. So by the end of this, I'm hoping that you guys can go out into the world and explain to a random passerby why global warming is happening and why it's a big deal and how we know humans are the problem. Dr. Love gave a very nice introduction. I really appreciated it. I'll just zoom through this because now you sort of know my career path, but I do think this is important for those of you that are thinking about going to graduate school and thinking about a career in science. It is, I think, useful to have a good idea of how people get to where they are. So I got to where I am by following this path of undergrad, PhD, postdoc, and then eventually a research scientist position here at NOAA. And generally, my research focuses on large-scale coupled climate variability and climate change, including how those two things impact extremes. So thinking about like precipitation extremes, which you experience all the time in Southern California, but also extremes in the ocean, things like extreme temperature or extreme changes in biogeochemical parameters like pH in the ocean, which critters, fish in the sea care about a lot. So I'm going to throw my email up here. I'll have it again at the end of the presentation, but please, please, please feel free to email me if you have any questions whatsoever, or if you just don't want to deal with Dr. Love when it comes to this material. So here's the brief agenda for what we're trying to do today. The goals today are to talk about radiation and climate change, to build that basic understanding of what radiation is, how it contributes to climate change and global warming. And we're going to use what's called a one-dimensional radiative transfer model, or a toy model, to build that understanding. And then secondly, we're going to discuss about how we know humans are responsible. So how do we know that humans are driving any kind of warming that we've experienced or any kind of increase in atmospheric gases that we can measure. And specifically, we're going to talk about something called the Seuss effect at the very end of the presentation. But before I get going, please feel free to interrupt me with questions. I do have sort of breakpoints in the lecture naturally built in to ask questions if you want to hold them, but also feel free to raise your hand and answer questions or ask questions. You can also type in the chat if you'd prefer that. That's totally fine. Also, please ask questions if you're confused. It's very hard for me to tell if anybody is confused because I'm not in the room with you. And also, this is kind of for me, like I really enjoy teaching, but this is mostly for you. So if you want to get something out of it and you're confused, please, ask the questions to get the understanding that you need. So let's talk about the climate system. I hope this animation is working for you. Someone give me a thumbs up if you see a video going. Good? Okay. This is the kind of data that I work with. This is a climate model simulation. These are not observations. This is not a satellite imagery kind of thing. This is a very high resolution climate model simulation. It's a computer simulation of how the atmosphere swirls around the planet. And this is just 1 year on Earth, basically. So you can actually see days passing on this climate model simulation. You can see these shadows passing over the land masses, right? That's nighttime, local nighttime, as the sun is moving from east to west on this plot, or on this animation. And you can see all sorts of complicated things going on. You can see clouds swirling around in Sahara, right? You can see this brown swirly stuff. That's dust getting advected off the Saharan desert over the open ocean. You can see all this green sort of misty stuff. That is the model representation of biomass burning. So this is our representation of people burning crops and those sort of burnt particulates getting into the atmosphere. You can see all the purple sort of swirly stuff coming off of North America and Asia. That's pollution, right? That's the model's simulation of industry, basically. And the reason why I'm showing you all of this is because I want you to be a little scared, right? This is a very complicated system. It's very hard to understand, and it's taken us decades to get to the level of understanding that we have today. And that's ultimately what I want to press upon you here, right? The climate system is a very complicated thing. It's made up of a variety of different components that all interact with each other. They all talk to each other. They all affect each other. And they include things like the cryosphere, which encompasses like sea ice, polar ice, permafrost, snow cover, mountain glaciers. All of the cryosphere is sort of getting smaller and smaller and smaller, but it does exist. We have the geosphere, which is like the land masses, the hydrosphere, ocean, lakes, rivers. That's more of my domain these days, is thinking a lot about the ocean. The biosphere, so ecosystems, animals, plants, us. We are part of, really, we affect all of these spheres, but we are generally part of the biosphere. And also the atmosphere, right? The atmosphere encompasses, the air we breathe, the air we fly in, and that's ultimately what I want to talk about today. I want to talk about the atmosphere, And I want to specifically talk about air and how it contributes to climate change and how it interacts with all of these other spheres through its interaction with radiation. So I do have a couple of questions for y'all for some general interaction. And I think probably the best way to do this is if people just type answers into the chat, and I'll just sort of read those, because that way nobody feels obligated to unmic themselves and speak up. So first question for you here is, what is in the air you breathe? So maybe just throw into chat some, if you can think of any gases that are in the air that you breathe. Good, bad, or indifferent. Oh my goodness, I see all sorts. Nitrogen, methane, carbon dioxide, water vapor, nitrogen, oxygen. Thank God we have oxygen, that's good. I see some argon in there, that's great. Okay, so I'm hoping that Dr. Love has already hammered this into your head, so that's good. What is in the air you breathe? You all nailed it. Nitrogen, right? 78% of what you breathe, when you go 78% of what you breathe is nitrogen. So it's not even oxygen, right? Actually, oxygen is the second most abundant gas in our atmosphere, right? It only takes up about 20% of the air you breathe. And it's actually really important to understand that, because oxygen, turns out that if you had any more oxygen in the air you breathe, it wouldn't be good for you. It'd be poisonous, right? You would get something called oxygen toxicity if you were breathing in more oxygen than about 20%. Anybody scuba divers? Anybody in this group? Raise your hand if you're a scuba diver, if you've been scuba diving before. A few of you maybe, okay. Well, if you've ever been scuba diving before, if you ever go scuba diving, there is a form of scuba diving that involves what we call enriched air, or what we call nitrox. It has more oxygen in the tank than a normal sort of parcel of air that you would breathe. It has as much as 36% oxygen in that tank of gas for scuba diving. And the reason that they do that is because as you get deeper and deeper in the water column, as you're diving, all of that water on top of you is exerting a ton of pressure on your body. And it turns out that if you have more oxygen in your blood, you're able to stay down deep under those pressures for a lot longer. But if you're down for too long, having that much oxygen in your blood is really bad, because that pressure will start to compress the dissolved oxygen in your blood into bubbles, and it'll basically clog your arteries and you'll have a stroke underwater. So it's really important to listen to your dive instructors if you ever go diving, and to take into account how much oxygen you have in your tank. So after oxygen, what else do we have? Well, it turns out we have argon. Argon is the third most abundant gas in our atmosphere, typically. It's about 1% of the air you breathe. Does anybody have any brave soul want to take a guess as to why we have argon in the atmosphere? In this case, you don't have to type it. You can just unmute yourself and take a stab at it. Any ideas?
Has it been there since ancient times?
Depends on how ancient we're talking about. Any thoughts? No? I'll give you a hint. Argon is the decay product of a different element. I don't know if you guys have talked about radiative.
From potassium, right?
Yeah, nailed it. I don't know who said that, but great job. Yeah, so there's actually, I'm sorry, go ahead.
Sorry, Jeanette did, sorry.
Jeanette, thank you. Yeah, so there's a ton of potassium in the Earth's crust. And so argon in the atmosphere is a byproduct of that potassium in the Earth's crust decaying over millennia. So over millions and millions of years, that potassium is radioactively decayed into argon, and it's being released out of the atmosphere. So it's slowly accumulating, and it's not a big deal. It's not poisonous to us. Actually, it probably would be poisonous to us in enough abundance, but it's never going to be so much that we have to really worry about it. We have a lot more pressing concerns when it comes to atmospheric gases, and that's because if you count up everything here, right, 78 plus 20 plus 1 is 99% of the atmosphere are these three things. What's that other 1%? Well, it's 1% stuff. And inside of that stuff, we have water vapor, which can range from anywhere from, well, this percentage is wrong. It actually can range from anywhere from 0% to 4%. I think I meant to put a hyphen instead of a decimal between these two things. Sorry, Evan, I see your hand raised. Please, yeah, go ahead.
So potassium, you said it radioactively decays. So it literally loses protons over time and then becomes argon?
Yeah, I mean, I'm not the chemist, but that is my understanding of the process. I don't know if Dr. Love wants to chime in on that one more too. I guess not.
Sorry, I was just Googling the periodic table. So argon, right. So yeah, the decay of phosphorus that's what happens. So when radioactive decay occurs, it's either emitting an alpha particle, which is helium, so that would be 2 protons, or a beta particle or whatnot. But yeah, it definitely it's emitting or ejecting parts of its nucleus, and then ultimately becoming smaller and becoming argon.
Thank you for the question. Yeah. So in that 1% stuff, we can have water vapor, and ignore that decimal. It's actually a hyphen. So water vapor can exist anywhere from 0% of the air you breathe up to 4% of the air you breathe, depending on where you live. So most of you are in La Mesa, outside San Diego right now, I would imagine. And La Mesa is without the city, La Mesa would be a desert, right? Southern California is just a desert if you're far enough away from the ocean. And because of that, you have really low relative humidity. You have very little water vapor in the atmosphere. So you're close to 0% water vapor a lot of the time. But if you lived in Brazil, if you lived in a tropical part of the world, next to a very, large rainforest, you can have up to 4% of the air you breathe can be dissolved water, not dissolved, sorry, gaseous water vapor, right? So there is quite a range depending on where you are in the world. Aside from water vapor, you can have carbon dioxide in the atmosphere, and this is pretty uniform no matter where you go in the world. Carbon dioxide makes up about 0.04% of the air you breathe, so about what we call 400 parts per million. That means if you have a million atoms or million molecules of air in a volume, 400 of them are carbon dioxide. That doesn't sound a lot, but by the end of this, I'm going to try and convince you that is a lot, and that has a big effect on the way that we live on this planet. Aside from carbon dioxide, you also have something like methane. Someone mentioned that in the chat. Excellent. Methane makes up about 0.00018% of the air you breathe, or 1,800 parts per billion. So that means if you had a billion air molecules, about 1,800 of those billion molecules would be methane. And that doesn't sound like a lot, but again, it is a very important gas in our atmosphere, as we're going to talk about today. And so what I'm ultimately going to try and convince you here by the end of this is that it is the jiggling, the changing, the wiggling in this 1% stuff from year to year, decade to decade, and century to century that ultimately drives all of the climate change that we experience. It's the less than 1% of the atmosphere. So in order to understand why that less than 1% of the atmosphere is very important, we need to understand what radiation is. So what is radiation? So in the chat right now, feel free to type in the first thing that comes to mind when you think about radiation. Danger, I agree. Movement of energy, that's a great answer. Wavelengths, scales, emitting energy as photons, light energy. Okay. It is a cause of skin cancer for sure. X-rays, yep. Nuclear, yep. Awesome. Okay, these are great answers. Does one brave soul want to unmic themselves and sort of define radiation for me without Googling it? Teaching with on the internet is difficult because you can always just Google the answer. No brave souls. Okay, that's okay.
We did cover electromagnetic radiation recently.
Okay, which is all forms of radiation. Okay, so radiation is energy traveling through space, and that's basically, I saw someone mention that movement of energy. That's absolutely right, right? Radiation is energy traveling through space, and by space I mean from here to there. It doesn't have to be literally in outer space; it can be on our planet too. Radiation is energy traveling through space, and we have to think about how energy or radiation is interacting with those constituents, those different elemental constituents that we have in air. So the nitrogen, the oxygen, the argon, and that 1% stuff. How does energy and radiation interact with those molecules? So we have the sun. It's this big burning ball of hydrogen in space, and it's emitting what we call solar radiation all the time, and eventually it reaches the Earth and it starts to interact with air molecules. What are the three things that can happen when radiation encounters matter? So in this case, the matter that the radiation is encountering are air molecules. So what are the three things that can happen? Throw them in the chat, or one person can unmute themselves and tell me. Can heat up. Okay, so heating up is another form. Another way to say that is absorption, pass through. Another way to say that is transmission, and reflect. Exactly, y'all nailed it, right? The three things that can happen when radiation interacts with matter is the radiation can be reflected or scattered in a different direction. And when this happens, it doesn't necessarily change the kind of radiation that exits the matter. So it doesn't necessarily change the wavelength of that radiation. It could pass through the matter without interacting with it at all. And we call that transmission. Another good example of transmission that is probably familiar to everybody is if you take an X-ray, right? If you get an X-ray of your arm, your skin, right, is matter, and X-rays are hitting your skin, but it's passing through your skin without interacting with it whatsoever. When it hits your bone, it gets scattered back, and that's what the machine is reading. So X-rays interact with calcium carbonate, which is your bones, but it doesn't interact with just your floppy skin. So it's two different kinds of matter, but two different interactions with X-rays, which are a form of radiation. And then the third thing that can happen is absorption, right? The radiation hits the matter, it gets absorbed by the matter, and if you're on the other side of it, you don't feel any of that radiation hitting you. It doesn't interact with matter beyond what it's absorbed. And the things that sort of determine, what happens when radiation is interacting with matter has everything to do with what we call degrees of freedom. So if you take like an air molecule, this is a molecule of, I believe, water vapor. I don't know. I'm gonna thanks for the confidence head nod, Dr. Lev. This is an H2O molecule, right? And its ability to reflect, transmit, or absorb radiation is completely dependent on how much it can move around, basically, whether it can stretch or bend or spin or vibrate, I guess. And we call these things, these axes of motion, degrees of freedom in a molecule. So not super important that you remember exactly all the jargon, but just knowing that whether a molecule can rotate or vibrate and how many axes that it can turn around really determines what kind of radiation it interacts with, whether it reflects it or absorbs it or transmits that radiation. Okay, another question for y'all then. So we have a decent feel for what radiation is. It's energy moving through space. What sorts of objects emit radiation? And you can type that in the chat for me. When you think about radiation being emitted by an object, what sorts of objects emit that radiation? Microwave, yep, microwave, X-rays. Select the machine, cell phones, unstable elements. It's a good answer. The sun, yep, the sun. We talked about the sun. I saw Toto's in there. All objects, yeah. Everything. Awesome. Yeah, we're definitely nailing it. Everything in the universe, and this is a very fundamental component of what I want y'all to take away from today's presentation, okay? Everything in the universe, you, me, this water bottle, my mouse, my computer, the walls in this building, you as a human, right? Everything in the universe that has a temperature is constantly emitting radiation in all directions all the time. And what do I mean by has a temperature, right? There are things that are very, very, very cold, but they still have a temperature and they're still emitting radiation. If something didn't have a temperature, it would be at what we call absolute zero. And absolute zero is where atoms stop vibrating. So temperature is just a measure of how fast atoms are vibrating. Yes, even an ice cube is emitting radiation, Dr. Lev. And if those atoms stopped vibrating at absolute zero or 0 Kelvin, then we would no longer be emitting radiation. But that is not observed. It's nothing can be at absolute zero. It's just sort of a theoretical concept. But everything in the universe is always emitting radiation at some wavelengths. And this is just sort of a summary of those two concepts, right? Radiation is energy traveling through space, and anything with a temperature is constantly emitting radiation all the time. And the only thing that controls the kind of radiation that an object is going to emit is its temperature, okay? And we call this kind of sort of the spectrum of radiation that you can emit and its relationship to temperature, the electromagnetic spectrum. And Dr. Love, I think, as you mentioned, you've sort of given a brief presentation on what this looks like, but I'm just going to show it to you again. This is the electromagnetic spectrum. It's the kinds of radiation. It's a very cartoony view of it, but it just gives you the highlights of what I want you to take away from here. You can see the different kinds of radiation that can be emitted out there. And you can see that they're all dependent on how fast that radiation is moving up and down. It's wavelength, basically. So the shorter the wavelength, the higher energy the radiation. So gamma rays are higher energy than, say, radio waves because they have shorter wavelengths. They're oscillating much, much faster. And the only thing that controls the kind of radiation that an object is emitting is its temperature. The hotter something is, the more likely it is to be emitting high energy radiation. So things like gamma rays and X-rays. The colder something is, the less likely it is to be emitting high energy radiation. So the colder something is, the lower frequency or the lower wavelength, the longer wavelength energy something is going to emit. things like radio waves and microwaves. And these little pictures are just giving you a sense of how big a wavelength is, or how long a wavelength is for a given source of radiative energy. So for something like a microwave radiation, you can think of the wavelength as something like the width of your hand, so like 10-ish centimeters. For something in the infrared or ultraviolet light, you get something like 400 nanometers to 800 nanometers is visible light. Ultraviolet light is closer to 10 nanometers. So these are very, very, very small. So not something that you could see with the human eye, basically. But let's think about things on things that interact with the climate system. Yeah, go ahead, Evan, please.
How come humans don't feel heat when they receive a medical X-ray?
That's a good question. Well, let's think about it, right? So if you get an X-ray and you see the bones in your body, your bones are absorbing that radiation, but your skin is not. It's being transmitted through your skin, so you don't feel it there. I would imagine that the blast of X-ray that you're getting from the machine is not enough for your bones to like heat up substantially. But if you sat underneath an X-ray for a very long time and you just kept getting pumped by X-rays for a very long time and your bones were constantly absorbing X-ray radiation, then you would start to feel it for sure.
Actually, Dylan, it wouldn't take that long. So that's the answer, is that the X-rays are infinitesimally short, right? And so I think a short period, we know this because you can actually fry a sample in an NMR spectrometer, and that's radio frequency. If you submit enough radio frequency to a sample, it'll heat up. So X-rays, if you hit something with X-rays for any length of time, it'll heat up pretty quickly. Of course, Dr. Meyer is exactly correct, though. It has to absorb it.
Okay, so let's think about objects. As I mentioned, everything in the universe is going to emit radiation, but let's think about objects that are important to moderating the temperature of the planet, the Earth. Okay, so let's think about the sun. Any ideas on how hot the sun is, where it might fall on the electromagnetic spectrum based on its temperature? How hot is the sun? Any thoughts? Don't Google it. Don't you Google it.
You're testing the 24-hour memory because we went over this yesterday.
Okay. I'm seeing a variety of answers. Some people are bouncing around it.
5,700.
Hot. Very, very hot. It's about 6,000 degrees Kelvin or Celsius, which is about 12,000 degrees Fahrenheit. So it's very, very hot on average. And because of that, because of its temperature, it sits here on the electromagnetic spectrum. The sun primarily emits ultraviolet radiation and visible light, what we call visible light. So visible light is radiation with wavelengths of 400 nanometers to 800 nanometers. And we only call it visible light because we've evolved as creatures to see it, right? And how do we know that the sun, right, is emitting visible light? It's because we can see it and we call it visible light. But what about the Earth, right? The Earth, by comparison, is significantly colder to the sun. Thank God. If it was very, very hot, we wouldn't be here. So how much colder is the Earth than the sun? Any thoughts in Celsius or Kelvin? It's about 300 Kelvin, someone's saying. Kayla? Any other thoughts, guesses?
The thing that amazed me is that the inside of the Earth is not that much cooler than the sun.
Yeah, the core of the planet is very, very hot. Liquid iron, and it turns out it takes a lot to melt iron. But yeah, the Earth is about 300 Kelvin on average. So the Earth sits on the electromagnetic spectrum towards longer wavelengths because it's colder. And so the Earth primarily emits in what we call infrared radiation. So infrared radiation is another way to refer to that as long wave radiation. Infrared radiation is the kind of radiation that anything at Earth-like temperatures is emitting all the time. So that includes you and me, everything in the room around you, your dog, your cat, my water bottle, everything at Earth-like temperatures is constantly emitting infrared radiation all the time, right? And we can't see it because we didn't evolve to see it. But there are some creatures out there that have evolved to see it. And this is what they would see if they were looking at infrared radiation. Their brains would see that radiation and convert it to something that makes sense. And they would see that hot places are warmer and cold places are cooler. So for example, on this kid, You can see his ears are typically colder than his forehead. So and this has all been converted to visible imagery so that we can actually see it. But the colder you are, the less energy you emit in infrared. So it's a colder color here. Whereas for a hotter forehead, because it's warmer, it's emitting more infrared radiation, and we see that as a hotter color. So things like snakes, right? Snakes see in the infrared. A lot of predators see in the infrared because they need to be able to see body heat in the dark to hunt, basically. So let's use this information. All right, let's use the information that the sun is primarily emitting in what we call shortwave radiation, so UV and short visible light. And let's use the information that the Earth is primarily emitting long wave radiation. And let's try to discern some things. Okay, so we're going to build a toy climate model, and we're going to try to reproduce the Earth's average surface temperature, globally average surface temperature. And we're going to do this two ways. Okay, we're going to try and reproduce it by first not having an atmosphere whatsoever, and then we're going to do it again, but we're going to have a very thin atmosphere, and it's going to have the same constituents of gases that we already talked about before. Okay, so let's do this. The sun, as we said, is very, very hot. It's about 6,000 degrees Kelvin, or about 10 to 12,000 degrees Fahrenheit. And because of that, it's primarily emitting what we call shortwave radiation, or ultraviolet or visible light. And that solar radiation is coming down through space. It enters our atmosphere, but this is going to be on a planet without an atmosphere. So it enters sort of the Earth, and then it hits the surface. It's absorbed by the surface, some of it, but actually about 30% of incoming solar radiation, or insolation is what we call it, about 30% of incoming sunlight never even interacts with the climate system. It just gets scattered back out to space. And we call that refraction albedo. So the albedo of the planet, on average, is about 30%. So what things on the planet reflect sunlight back out to space? Any ideas? You can throw it in the chat. Clouds, snow, ice. Yep. A lot of cold things, right? Ice and snow. Yep. Perfect. So clouds, snow, ice, but also sand. Sand also has high albedo. Basically anything bright, right? If you go outside and you're blinded by something because it's really bright, it has a high albedo and it's scattering sunlight out to space. A very important point here is that cities, so concrete, has a higher albedo than forests, right? Forests are dark green and cities are sort of a bright gray or beige, right? So cutting down forests, dark green forests, and replacing them with cities actually increases the albedo of the planet because you're scattering more sunlight back out to space. So 70% of that incoming solar radiation is going to be absorbed by the Earth's surface. The Earth's surface is going to heat up. And because it's at Earth-like temperatures, because it's much, much cooler, right? The Earth is something like 288 degrees Kelvin, about 300 degrees Kelvin, which is on average about 60 degrees Fahrenheit. Because it's much, much colder, it's primarily going to emit that radiation back out at what we call long waves. So infrared radiation is going to go back out to space. Okay, so we have a balance, right? We have outgoing long wave radiation has to be balancing out incoming solar radiation or insolation. So we have a very, very simple equation here, right? We have incoming solar radiation has to equal outgoing long wave radiation, and a very, very fundamental component of physics is conservation of energy, right? What comes in has to equal what goes out. You cannot destroy or create energy, right? So we have something coming in from the sun, it has to go back out to space via outgoing long wave radiation. So I'm not going to show you the gory details of the equations, but basically there's a temperature. There's the temperature of the Earth is in this set of equations, and you can solve the equation to figure out what the temperature of the Earth has to be to make this true, right? Because if you increase the temperature of the Earth, you're going to increase the amount of long wave radiation going back out to space, and that will help to balance. It'll help to balance the amount of solar radiation coming into the planet. So if you do that, right, if you set these two things equal to each other, solve for the temperature of the Earth has to be to make this true, you end up getting an Earth-like temperature of about -2.5 degrees Fahrenheit. That is the temperature the Earth would have if we did not have an atmosphere. That's all the Earth. That's the only temperature the Earth would have to have to balance the amount of solar radiation that we get at any given point on the planet. And keep in mind, this is an average temperature over the whole globe. So some places would be warmer than this, but some places would be much, much colder than this. But this is very unlivable. How do solar flares affect this rate? That's a great question. We're going to talk about solar variability a little bit later. But that is a good question, Aaron. Thank you. So this is not what we experience, right? We live on a relatively comfortable planet. that is not on average minus 2.5 degrees. So let's do this again, right? Let's do this experiment again. And we're going to make our climate a little bit more complicated by adding the atmosphere. We're going to add the atmosphere specifically with these constituents, right? We're going to have an atmosphere that has 78% nitrogen, 20% oxygen, 1% argon, and very importantly, 1% stuff. Okay, and so if we do that, let's think about how radiation from the sun is going to interact with this new matter, right? Because before our atmosphere didn't exist. There was no matter. There was nothing for the sun to interact with until it hit the surface of the Earth. So now the sun has something to interact with. It has the molecules in our atmosphere. So which of these gases are good at interacting with shortwave radiation? Any ideas? And shortwave radiations, again, just as a reminder, is the stuff coming from the sun, so UV and visible light. Do any of these gases interact with shortwave radiation? And if so, which? Water vapor, maybe? Actually, that's not wrong. Water vapor does interact with solar radiation. Maybe I'll be more specific. Which of these gases is good at absorbing shortwave radiation, not just interacting with it? Because water vapor does scatter sunlight, and we know that because clouds are made of liquid water, and they scatter light back up to space. But which of these are good at absorbing shortwave radiation? I'm seeing some answers come through. CO2. Let me.
And Dylan, just to be clear, so when you say shortwave radiation, you talk about visible and ultraviolet, not infrared, correct?
Correct. Yep. Correct. Okay. I see a lot of CO2s, and this is a very common misconception, and it's kind of a trick question. Turns out all of these gases are bad at absorbing shortwave radiation. They're all terrible at it, right? And we know this, right? We should intuitively know this because when you step outside, you can see stuff, right? If any of these gases were good at absorbing shortwave radiation, none of the radiation from the sun would make it to the planet's surface, right? It would be very cold for one thing, but it'd also be very dark, right? None of that visible light would be hitting the ground, would be hitting your clothes. You wouldn't see anything being scattered to your eyeballs. So if oxygen was good at absorbing shortwave radiation, there'd be nothing to see. You know what I mean? But this one's not a trick question. Which of these gases are good at absorbing long wave radiation or infrared radiation, the kind of radiation that we all emit at Earth-like temperatures? Any ideas? There is a real answer to this one. Oxygen, maybe? All of them? CO2, nitrogen? I'm seeing a smattering of answers. Okay. So it turns out that this less than 1% stuff, so the 1% of our atmosphere that's made up of something like water vapor, carbon dioxide, methane, and some other stuff, this less than 1% of our atmosphere is extremely good. It's very efficient at absorbing long wave or infrared radiation. This other 99% of our atmosphere is just like meh, right? Long wave radiation just passes right through oxygen. It just passes right through nitrogen. It doesn't interact with it at all. But water vapor, CO2, and methane are three gases in the atmosphere that do a very good job at absorbing infrared radiation. And there's a law of physics that say if something is a good absorber, it's also a good emitter at a very similar wavelength. It's called Kirchhoff's law. So let's add an atmosphere into our toy model, and let's give it these atmospheric constituents. Let's give it these gases, and let's also give them the radiative properties of these gases, okay? I see a question, but it's cut off. Let me pull it up here. So is this why methane is more harmful than CO2 emissions? That's a great question, Jeanette. If I don't return to that question, the answer is yes. Both CO2 and, actually, I guess I can answer that now. It's not really a spoiler. Both CO2 and methane are very good absorbers of CO2, or sorry, of infrared radiation. Methane is much better. It's about 1,000 times more efficient at absorbing methane is about 1,000 times more efficient at absorbing infrared radiation than CO2, but it's also a lot less abundant. So CO2 is really important because it's just it's several orders of magnitude more abundant than methane, but methane is also several orders of magnitude more efficient at absorbing infrared radiation. So it's also a very important gas that we like to think about. But we're jumping a little bit ahead. Let's just plug in this atmosphere into our little toy model and see how it affects the outcome, how warm the planet would be. Let's go forward. There we go. Okay, so we have an atmosphere, right? We have our Earth's surface. This atmosphere is going to be transparent to shortwave radiation because none of those gases interact with incoming sunlight. All of that sunlight is going to hit the surface. 30% of it's scattered to space, but 70% is absorbed at the Earth's surface. It's absorbed at the Earth's surface. The Earth is much colder than the sun, so it's going to emit that radiation back at long waves or infrared radiation. And now we have an atmosphere that we're going to say is completely opaque to long wave radiation or infrared radiation. And by opaque, I mean that infrared radiation is going to encounter that less than 1% stuff, the water vapor, the CO2, the methane. It's going to get absorbed by those molecules because they have, lots of degrees of freedom. They can rotate, they can bend, they can vibrate. They absorb that infrared radiation. And because they have a temperature, because they're a thing in the universe and that has a temperature, they also emit radiation. And when they do, it's going to also be at infrared wavelengths. And it's because they're also at Earth-like temperatures, those molecules. So they're going to emit radiation in all directions. And importantly, up to space. So that's going to help balance the equation, right? Some of that radiation is going out to space, but also some of that radiation is coming back down at the Earth, where the Earth's surface is going to absorb some of that infrared radiation coming from the atmosphere. So now we have a new equation, right? It's no longer just incoming solar radiation is balancing outgoing long wave radiation. We now have an equation where incoming solar radiation plus incoming atmospheric long wave is being balanced by total outgoing long wave at the top of the atmosphere. So now, again, without going into the gory details of what the equation actually looks like, we can solve for what the temperature of the Earth would have to be to make this true. And again, it has to be true because it is a law of physics that you cannot destroy or create energy. It has to be balanced. It's conservation of energy, right? So who thinks, just show of hands here, who thinks that the Earth is going to be colder than before? Where before it was about -2.5 degrees Fahrenheit. Raise your hand if you think it'll be colder than before. Any thoughts? Okay, raise your hand if you think it's gonna be warmer than before. Okay, I see a lot of raised hands here, so that's awesome, right? The temperature of the Earth is now, on average, gonna be about 80 degrees Fahrenheit. So that's actually much warmer than what we experience now, but it is much closer to the observed temperatures that we actually see from day to day here. And it's all because we added a very thin atmosphere. Go ahead, Dr. Love.
Yeah, sorry. So Dylan, I know you probably said this, but this is all based on modeling?
This is based on theory. You don't need a model to do this. I'm just sort of illustrating.
Right, no, I mean the number, because I thought the average was 57.
Oh, that's observed. So this 80 degrees Fahrenheit is balancing the equations. It's
so
not
that's pretty cool. That's when the model or theory matches reality. That's pretty neat.
Yeah, exactly. And the atmosphere is increasing the temperature, right? It's acting as an insulating feature in our climate system. And what do we call this thing, right? We've all heard the phrase before, right? This is the greenhouse effect. The atmosphere is insulating the planet. It's keeping us warmer than we should be, just based on the amount of sunlight that comes in. And this is a good thing, right? That greenhouse effect is a good thing. We just saw it. If we didn't have the greenhouse effect, we would live on a planet that's much colder and not livable than we experience today. But as they say, too much of a good thing can sometimes be a bad thing, right? So this less than 1% stuff in the atmosphere are what we call the greenhouse gases. These things are very good at absorbing infrared radiation, and any change in the amount of these gases in the atmosphere can lead to, an enhancement of the greenhouse effect. Specifically, let's think about carbon dioxide. This is a time series, so it's showing you the concentration of carbon dioxide in the atmosphere, measured from a volcano in Hawaii called Mauna Loa, from about 1958 to today. And by today, I mean July 5th of 2022. So it's a very near real-time measurement. And you can see that the concentration of CO2 today is about 420 parts per million. But about 60 years ago, it was only about 315 parts per million. So in about 60 years, we've increased the amount of CO2 in the atmosphere by about 0.01%. So that doesn't sound like I'm sorry, it's increased by about 25%, but it's gone from 0.03% to 0.04%. So again, it sounds like a very small amount, but CO2 is such an efficient absorber of infrared radiation that this has a huge impact on the greenhouse effect. And by the way, this time series is famously known as the Keeling curve. It was named for David Keeling, who is or who was a scientist at Scripps for his whole career, basically. Scripps up at UC San Diego, and now his son Ralph Keeling is running the Keeling Lab at Scripps and maintains these instruments and maintains these measurements for so that we have a good idea of where CO2 is headed around the globe. And I will say, as Dr. Love has mentioned, yeah, go ahead, Dr. Love.
Sorry, I was going to wait till you were done with this. So
sure. As Dr. Love mentioned, I've given this presentation to his classes before, and every year I update this slide to represent this year's measurements. And I don't, for whatever reason, I don't have the slides from the past couple years, but I have it from 2018, June 26, 2018, the concentration was 410. We can go back one more year to June 27th in 2017, and it was 408. So you can see that just in 5 years, we've increased it by 10 parts per million around the same time of the year. So I'm just trying to give you a sense of how the rate of increase in real time as we're seeing this unfold before our eyes. It's very big deal. Go ahead, Dr. Love.
So I was wondering if you can, and you may not know this, but it seems like there's a seasonal wiggle or some kind of wiggle in this. Do you know what that might be due to?
Yeah, yes. The wiggle is a seasonal cycle. CO2 is drawn down by plants and fauna, right? And us, right? We breathe, well, plants breathe in CO2 and they spit out oxygen, right? That's photosynthesis. So the seasonal minima, and I'll back out here, the seasonal minimum in CO2 happens in like November and December, and that's like after the northern hemisphere has experienced all the greening from the spring and the summer. It's drawn down all that CO2, and then eventually the plants die. And once the plants die, CO2 starts to build back up in the atmosphere, and we get a seasonal maxima in CO2. So these ups and downs are because of the seasonal cycle of plants, basically, specifically in the northern hemisphere, because there are more plants in the northern hemisphere than the southern hemisphere. Okay.
It also lends additional credibility to the graph, right? There's another bit of reality data in there. That's cool.
Yeah, definitely. Okay, so if we increase CO2 in the way that we've observed, that thickens the atmosphere in a way. And I say thickens because it's not literally getting thicker, but there are more CO2 molecules in the atmosphere, and this enhances the greenhouse effect. It increases the amount of infrared radiation that the atmosphere absorbs and re-emits back at the surface, and it increases the temperature of the planet. So a very important question is, what else besides increases in CO2 and other greenhouse gases affects surface temperature? Okay, and I'm going to sort of zoom through these next few slides because we're running out of time, and I want to make sure we get to the Seuss effect at the end. You're going to get these slides, so don't worry about taking any notes on this last couple parts here. So let's think about what else affects surface temperature, because I've presented a very simplified view of the Earth's energy balance. There are a lot of things. Everything on this plot interacts with sunlight, basically, and impacts the amount of energy that the Earth is absorbing and emitting back out to space. So let's just talk about a few of them very briefly. Someone mentioned earlier, how do solar flares impact the amount of energy coming to the surface? The sun does go through sort of natural cycles and how much energy it's emitting to the planet. And this can vary from year to year and decade to decade and century to century. And these natural solar cycle variations can influence the amount of energy that the Earth absorbs, because it influences basically the size of this arrow, right? It changes incoming solar radiation at the surface. So what would this do to our surface temperature if we didn't change anything else? It would warm or it would cool the planet. If you increase the amount of solar radiation, you would warm the planet. If you decrease it, you would cool the planet. What else can affect the temperature of the Earth's surface? Something called aerosols. So aerosols are tiny solid particles that you can find in the atmosphere, and they are generated from pollution. So your car is going to spit out aerosols into the atmosphere, or from industry, right? Our power plants are spitting out aerosols into the atmosphere. Volcanoes also spew a ton of aerosols into the atmosphere. And what these do, these aerosols are very shiny. They're at just the right size that they're very good at scattering infrared or scattering solar radiation. They're very reflective. So if solar radiation hits a bunch of aerosols, it'll get scattered back out to space, and it increases albedo. So what would this do to our surface temperature? It would act as a cooling on the surface, right? Because you're increasing the amount of radiation scattered back out to space, reducing how much is absorbed at the surface, and causing an overall cooling on the Earth's surface. What else? We can think about ozone. So ozone in the stratosphere. So the stratosphere, you can break up the atmosphere into different layers. We live in the troposphere, which is about 0 to 10 kilometers above the troposphere is something called the stratosphere. It's another layer that's characterized by this, what we call the ozone layer. So ozone is O3, it's a molecule. And ozone is a very good absorber of shortwave radiation, specifically shortwave radiation in the ultraviolet part of the electromagnetic spectrum. It's basically the Earth's sunblock, right? You go outside, you put sunscreen so you don't get burned. You're getting burned because you're absorbing infrared or UV radiation. The Earth has this ozone layer, and that's its sunblock. It stops a lot of that harmful UV from reaching the surface, and UV is very energetic. So if it did reach the surface, it would warm the planet more. In the 80s, we noticed that chlorofluorocarbons, or CFCs, were destroying ozone in the stratosphere. And these were chemicals, man-made chemicals that came in aerosolants, so like hairspray or refrigerants, so completely manufactured, not natural in the climate system at all. And they destroyed ozone, created this ozone hole, which allowed more UV radiation to reach the surface, and this causes a warming overall. So let's think about these different, what we call climate forcings, right? If we increase CO2 and other greenhouse gases, this would lead to a warming of the surface. You could change how much solar radiation is coming into the planet. That could cause a warming or a cooling, depending on where we're at in a solar cycle. You could explode a volcano, right? That generates a ton of aerosols, and that would cool the surface of the planet. Pollution generates aerosols as well. That also acts as a cooling. And then ozone depletion in the stratosphere specifically allows more UV radiation to come to the surface and causes warming. So the question is, what's winning? All of these things are tugging at the system and trying to cause a warming or a cooling, and one of these is going to win out eventually. So what I'm going to show you here is an animation of surface temperature as a function of month and year, and it's going in a circle here. So it's going from January in a circle clockwise to December, and every loop is a year, and it's going to show you the surface temperature difference of the planet from the beginning of the record to the end for every year. What do we notice, right? We see that the circle is expanding. The farther you get away from the center of the circle, the warmer you are. So you can see as the circle is expanding, the planet is getting warmer and warmer and warmer. We also might notice that after about 1950, the rate at which this circle is expanding increases. You can see that it accelerates right about maybe in the 70s here. So you can see how it's expanding much faster, right? This is global warming, right? That's what's winning. The increase in CO2 in the atmosphere and other greenhouse gases is winning among all these other climate forcings. And we've experienced about a 2 degree Fahrenheit warming globally averaged since 1860. And if you're interested in looking at the updated version of this circle, this only goes to 2016. But if you want to look at the most recent one, it's called the Hawkins circle, which you can just Google and it'll pop up.
Dr. I just want to interject something. The one thing to notice here is that overall it's increasing, but you'll see it grows and shrinks and grows and shrinks. And you'll hear some politicians say, oh, it's actually cooler this year. But overall, you have to look at the data as an aggregate. Overall, since the Industrial Revolution, it definitely has increased by 2 degrees.
This is a very good point about the difference between weather and climate. It's very important to realize that you can have a cold winter, but global warming is still a thing. So it doesn't make any sense for a congressperson to go into Congress with a snowball and say, hey, global warming can't be a thing because it's snowing outside. That's not a thing. Weather is the thing you experience on day-to-day sort of noise, and climate change is what that noise is riding on. Over a long time, you can see that all the warm and all the cold have slowly gotten warmer and warmer and warmer. So it's very important for everybody to separate the difference between weather and climate in their minds. But so on average, we've experienced about 2 degree Fahrenheit warming since 1860. But this is something that's sort of lost in the media and the way we communicate global warming and climate change is we like to use these globally averaged numbers, but they're not necessarily representative of what an individual is going to feel at any given location, because nobody lives in the global mean. Nobody experiences the global mean. So we can think about how temperature has changed in space since 1860. And this is in degrees Celsius. If you want it in degrees Fahrenheit, just multiply it by about 2, and that's roughly where you're at. You can see that there are some places in the world that have warmed much faster than other places in the world. So there's like Siberia has experienced almost 7 degrees Fahrenheit increase in temperature. Same is true for Canada, the high Arctic areas of Canada. Brazil has experienced quite a bit of warming, almost 5 degrees Celsius of warming over the last 100 years or so. The Southeast United States has not experienced all that much warming, but the western part of the United States has. It's experienced more than the global average. Particularly Southern California has experienced a lot more warming than the global average. So what you experience in La Mesa is going to be very, very different and probably more intense than what someone in Georgia is experiencing.
It's true, but a friend of mine had a business called Sunny in 72, because in the past, when people ask, what's the weather like in San Diego? It's sunny in 72. Now I say it's sunny in 82.
I mean, that's kind of a thing. And it's these differences in the way we experience global warming that really makes, doing anything about it very difficult, right? Because there are people in this on the planet who don't experience these impacts as strongly as other people. So for them, it's not as visceral, right? They don't feel that same sense of urgency to do something about it because they're not experiencing it in the same way. I saw someone ask, what's that cold spot south of Greenland? This is called the warming hole. It's actually kind of complicated, but I guess the short version is there is a very very large ocean current system that begins south of Greenland. It's where a lot of water is actually coming from the surface and going down into the deeper parts of the ocean. It's called the Atlantic Meridional Overturning Circulation, and basically what's happening is that a lot of heat is being absorbed at the surface of the ocean, but then it's getting subducted down into the water, down deep into the water column. So you're not actually experiencing all that much warming because it's constantly getting replaced by cool water. So this all jives with our understanding of the dynamics of the ocean, basically. So I just want to quickly also look at the same idea, but for the United States. As I mentioned, the Southeast United States hasn't experienced all that much warming, but the Western United States has experienced quite a bit, much more than the global average. And you are all reaping sort of the consequences of all of that, given the drought that you're experiencing right now. I see Lindsay's asked a question here. What causes certain areas to get warmer faster? And Gabrielle had the same question. That's a great question. Some places are going to warm faster based on what we call feedbacks. So we know that high latitudes closer to perennial ice sheets, so like Greenland and the high parts of Siberia, the high latitude parts of Canada, those places are going to warm much faster than other places because of something called the ice albedo feedback. So let's say you have a sheet of ice. It's very reflective. Sunlight comes down, it hits that ice, and a lot of it gets scattered back out scattered back out to space. Some of it is absorbed. Most of it is scattered. If you melt that ice, because you've increased CO2 in the atmosphere, if you melt that ice, you're now replacing that shiny land surface with just grass or ocean. And now you're absorbing more because you have, something that's dark at the surface, you're absorbing more solar radiation because your albedo is lower, which causes you to warm faster, melt more ice, lower your albedo, absorb more, melt more ice. So you can see how this is sort of a runaway positive feedback. It's called the ice albedo feedback. There are a lot of feedbacks on the planet. It's more than I can explain in a single talk, but that's one of them. Also, another thing that affects the rate at which places warm is the atmospheric and oceanic circulation. There are some places where temperature is moved around in a certain way. It's pretty complicated, but I'm happy to give you like a more satisfying answer over email if you don't mind, because we are running a little bit out of time here. And I want to make sure we get to the Seuss effect. Jeanette, I do see your long question. I'm going to read it and I'll try to get to it at the end. Okay. But I appreciate you asking a question and put it in the chat. I'll make sure I get to it at the end. So I do have a sort of a natural spot here for questions. But as I said, we only have about 15 minutes and I want to make sure we get to the Seuss effect. So I'm going to push through. There'll be another spot at the end for questions. But let's talk about this. All right. So we've talked about radiation. We've talked about climate change. We've built our one-dimensional radiative transfer model, our toy model. And now the question really is, how do we know for sure? How do scientists know? How do we know that humans are responsible for the changes that we've observed? It's through this thing that we call the Seuss effect. And a very important question is here, we see this increase, we see this observed increase in carbon dioxide. And we know based on theory and observations and tons of lab studies that increasing CO2 will increase the greenhouse effect and warm the surface of the Earth. But we also know through very careful study and observations and lab work that CO2 has varied in the past. It's been higher, it's been lower. So how do we know that this increase that we're observing, excuse me, how do we know that this increase that we're observing is due to, say, the burning of fossil fuels and not just something that naturally happens in the climate system? So yeah, our CO2 change is really driven by humans, because it has, as I said, varied in the past. For example, we have scientists that go to Antarctica, they go to Greenland, they go to mountain glaciers, they drill way down into these ice sheets, and these ice sheets can be very, very thick, almost 2 kilometers thick. And they drill what are called ice cores. And what's really cool about ice sheets is the way they're built. So basically what happens is if you have snow on an ice sheet or any surface, that snow is going to be very fluffy, right? There's a lot of air in snow. But over time, if you have lots and lots of snow year after year, you're going to have one snow layer being piled on top of another, on top of another, on top of another. And over time, the weight of all that snow is going to compress the bottom layers until they form a single ice sheet. And when that happens, you actually trap air pockets in the structure of that ice sheet, and you capture little air bubbles inside the ice. So these ice cores are full of air. They're about 10% air by volume. And if you take a little sliver of an ice sheet, you can see these thousands and thousands of air bubbles that were created when the snow was getting compacted down over thousands of years of snow. And what's really cool is that you can melt these ice cores down, and you can measure the gases that come out of those air bubbles and get a direct measurement of what carbon dioxide was over, up to about 800,000 years ago. The oldest ice that we have from Antarctica is 800,000 years old, and we can get direct measurements of CO2 up to about that time. And I have to impress upon you here that these are not guesses. We're not guessing that what the CO2 concentration is. We're directly measuring it from these paleo air pockets, basically from the ice. And we can see that carbon dioxide has varied in the past, right? We see that it's gone from about 200 parts per million to almost as high as 300 parts per million. But what's really important here is the sense of scale, right? For example, you can see that there's almost 100 parts per million increase in CO2, but it took about 50,000 years to do that naturally. Currently, we are way up here on this scale. Okay, this is today's CO2 measurement. This is the Keeling curve we talked about, but now we're at 400 parts per million, and we've seen 100 parts per million increase in CO2 in the last 60 years. So that by itself should be a red flag, right? Why would we be having these natural carbon cycles on these 50,000 year timescales for 800,000 years, and then suddenly the Earth's like, okay, let's just ramp it up for whatever reason. So that's automatically a red flag. But we can be a little bit more scientific about it, right? How do we this still doesn't prove anything. It doesn't say that humans aren't responsible or are responsible. So how do we know for sure? Well, we have to think about isotopes. So carbon comes in a variety of different flavors, right? It comes in different, what we call isotopes. And isotopes are just versions of atoms with different numbers of neutrons in their nuclei. If you have more neutrons in your nucleus, it doesn't change the balance of charges within the atom, but it does change its mass. So CO2 can be made up of what we call either heavy or light carbon isotopes. So a heavy carbon isotope is what we call carbon-13. A light carbon isotope is what we call carbon-12. And the way that these isotopes interact with nature are a little bit different. So we know that on our planet, right, plants do this beautiful thing that we call photosynthesis. They draw down CO2, they spit out oxygen, and critters like us, biofauna, right, we breathe in oxygen and we spit out CO2. It's a beautiful dance that evolution has created for us to be able to survive. But it's really important to realize that nature is very lazy, right? We preferentially take up lighter carbon isotopes because it's easier. It takes less energy to fix it to our structure. So a plant, a tree, when it takes in CO2 from the atmosphere to build its sugars, to convert it into glucose and to produce energy, it's going to preferentially take up CO2 molecules that are built up of these light carbon isotopes, the C12. And then animals, when they eat the plants, right, we're eating plants or other things that have eaten plants, and they're going to, we're preferentially going to fix that light isotope carbon into our physical structure because we're lazy. It's just easier for nature to do it. And so we call things that are alive, plants and animals, isotopically light because we're full of these light carbon C12 atoms, basically. And if you take enough of these light isotopes from the atmosphere away, you leave the ambient air, so just air, isotopically heavy because the air is going to preferentially have more carbon C13 than biofauna, right? It's going to have a larger ratio of carbon-13 to carbon-12, basically. Okay, so that sort of sets the stage, and now let's fast forward, right? Plants and animals die, and as they die, and over the course of millennia, sediment starts to build up on top of them, right? And as you increase the amount of stuff on top of them, they get crushed, they get built down, they get broken down, they turn into goo, and we call that goo oil. And oil, because it's built up of the same carbon atoms that those plants and animals were made of, is isotopically light because oil has more carbon-12 than it does carbon-13. It's just isotopically light. So how does oil return to the atmosphere where it can interact with the carbon dioxide that's causing the greenhouse effect? Well, naturally, on natural timescales, volcanoes tap into oil reserves and they spew it back out in the atmosphere as eruptions, and we get a ton of CO2 from volcanoes. And that takes a long time to do. That takes about 50,000 years for the whole cycle to overturn. But humans, in our infinite wisdom, have dug down into the earth, found oil, and we've used it for industry, right? We've short-circuited the carbon cycle by digging down in these oil reserves, burning it, and releasing that CO2 in the atmosphere. And so there's a very important thought experiment that can be had here, right? If recent CO2 increase is due to the burning of fossil fuels, so if it's due to the second path here, then carbon in the air, carbon in the atmosphere, this ambient air, should become isotopically lighter over time. And by that, I mean you're taking the light isotopes, all that C12 in the oil, and you're releasing it into the atmosphere where there's usually a lot more C13 than C12. So you're taking something that's heavy, mixing it with something that's light, and you should end up with something that's lighter than before. And another way to think about it is if you mix something that's really hot with something that's really cold, you end up with something that's warm. It's the same idea, but think about weight in this case. And you know what? That's exactly what we see. So this yellow curve is just sort of, so the x-axis on this plot is showing you time from the year 1000 to about today. The yellow curve on this plot is showing you basically the weight of air in the atmosphere. So higher up is heavier and lower down is lighter. And then the black line is showing you, again, the concentration of CO2 over the last 1,000 years. And so what do we see? We see that concentrations in CO2 have increased dramatically over the last 1,000 years, particularly in the last about 150 years. And you can see a very stark corresponding decrease in the weight of air as more C12 isotopes are being released into the ambient air. We call this thing the Seuss effect. And so this is, for scientists, this is the smoking gun. This is how we know definitively that the increase in carbon dioxide in the atmosphere that we've observed in the last 100 years is coming from the burning of fossil fuels, because fossil fuels are isotopically light. They're mixing in with all the heavy ambient air, and we're resulting in something that's lighter than before. And fun fact, Seuss was a doctor, Dr. Seuss, not the Dr. Seuss, but he was a doctor at Scripps. So this is all also coming from Scripps up the road from y'all. So that's it. That's all I got. How do we do on time? Cool. We got about 10 or five-ish minutes to talk about questions, but here's my email again. Please feel free to email me if you have any other questions about any of the material we talked about today. I'm happy to take any and all curiosities that you might have from here. So thank you very much.
First, I'd like to thank Dr. Amaya for yet again another really amazing presentation. And I love, dude, man, you gotta figure out how to teach a course at UC Boulder or somewhere, because you're super phenomenal and clear, understandable presenter. So thank you very much. There's some questions in the chat, and people can ask questions live. And your timing is perfect, by the way. It's 11:10, so you timed this perfectly.
Awesome. Do you want to moderate questions from the chat, or do you want me to just sort of go down?
So what would be something that consumes C13 instead of light carbon? I don't know.
So I'm being very general here. Nature is lazy, but it doesn't mean nature doesn't take up C13. Plants do take up C13. They just preferentially take up more C12 than C13. So C13 is not inert. It is being interacted with by everything that takes up carbon dioxide, but plants are just better at taking up C12.
Another question from Matthew Patterson. Could the temperature change lead to a collapse of the Gulf Stream / other ocean currents? How would this affect future increases in temperature? Is this taken into account in temperature prediction models? So future global warming absolutely will change the way that the atmosphere and the ocean circulate.
and move heat and energy around. The Gulf Stream is part of what we call the Atlantic Meridional Overturning Circulation. It moves heat and energy from the tropics to the cold poles, and AMOC brings it down at depth back to the tropics. So there's a big overturning. There is a lot of good research to suggest that as the world gets warmer and warmer, AMOC will become increasingly less important from an energy balance standpoint. So it could slow down. So the Gulf Stream could slow down. Implications of that meaning would be like Western Europe would get much colder than it is today. If you've ever been to England, or if you are at all familiar with England, England is much warmer than it should be, given its latitude. And that's because the Gulf Stream is transporting a lot of hot water to that area, and it's keeping it nice and temperate. You stop the Gulf Stream or you slow it down, you're really gonna cool Western Europe. So that's a very important point. And we do think about these in our climate models, or what you refer to as our temperature prediction models.
Lindsay Lehman had the same question that I had. So are the same ice samples, those ice cores, is that what was used to measure the CO2 over the last 1,000 years for the SUS data?
Yeah, so that black curve on the SUS data is coming from ice cores for sure. The yellow curve is coming from a combination of ice cores, but also ambient air measurements from modern day CO2 measurements. So it's a combination of the two. But it's all, I'll stress again, it's all a direct measurement of the atmosphere. Those air pockets are not, we're not guessing what CO2 was. It's exactly what it was in those air pockets.
Could you go back to that slide?
Sure.
So yeah, I'm looking at the error. So the error bars are reasonable. That's what I was looking at to see. But I was wondering what the what differences in C13, C12 ratios we're talking about, if they're like really tiny, but it looks like whatever they are, the error is definitely not huge.
Right, and you can see how the error goes down once we get to like the modern day record. As you get closer and closer to like present day, the error bars get smaller and smaller because our machine precision is better for better for real measurements.
What do you think is the max concentration of CO2 that we can reach before it causes irreversible effects? We may be there already now.
Yeah, we're there, team. Your kids, my kids. I'm having a baby in November. Their kids, we're there. The issue with CO2 is it has a long lifespan in the atmosphere. It lives in the atmosphere anywhere from 50 years to 1,000 years, depending on what's going on around it. So what that means is that we could stop emitting fossil fuels today. We could stop driving cars, flying in planes or using power plants. We could stop today and we would still feel an increase in warming for, a century long, at least, because CO2 is in the atmosphere, it's going to be there. So there are a lot of irreversible impacts that we're experiencing now. I personally believe that like the Southwest United States is like it's there. It's happening, y'all. If you think about like Lake Mead, it's almost at the high water line. Y'all are in a very unprecedented drought. It's not a great time to be there, unfortunately. But the impacts will become increasingly irreversible all over the globe, in the next 50 to 100 years. I mean, it's here. We're doing it.
How do man-made materials contribute to absorbing heat, if any measurements? Jeanette said, I'm thinking about asphalt and how it creates hot pockets in the city.
Yeah, so there's definitely like the urban heat island is a thing. Cities are much warmer than the surrounding area that are separated by forests. Plants have a lot of moisture in their leaves, and they evaporate that water, and that evaporation cools the area around it. So a forest is almost always going to be much cooler than a city. Another good reason why that is because plants are green and they absorb more solar radiation, but cities are typically asphalt or concrete, and concrete's pretty shiny. So a lot of that solar radiation is getting bounced back at you and absorbed in your skin. So cities are typically like 5 to 10 degrees warmer than the surrounding area because of those effects.
Could we seed the stratosphere with short-range radiation reflecting components to help decrease the increasing temperature rate? And Aaron also says, congratulations on becoming a dad. Thank
you, Aaron. I appreciate that. We could, in theory. You're talking about geoengineering. It's something that we research actively. We, as in the community, is researching actively. No one knows how to do it well enough or nobody's confident enough in the process yet to do it, because we don't know what the downstream effects would be. Basically, we don't know what the unforeseen circumstances might be that might cause, other issues around the globe. So that technology is not quite there yet to be viable.
So we're at 11:16. I'm going to jump to the final questions. And Dr. Maya, if you could go to your final slide just so you can have your email available. So Valeria asks, what do you think we can do today to help fight climate change and global warming? And I'll let you know, Dr. Maya, we had a presenter talk about the human population, and there's a chart that shows all, like, never drive a car, don't use hot water when you wash your clothes, don't use a dryer, don't do this, and it tells you all the amount of CO2 that you won't be putting into the atmosphere. And then in the middle, the biggest circle is have one less child.
Yeah.
And that's the big issue. So, but what do you think? What do you think?
So there's actually good evidence to suggest, so population rates or birthing rates are declining, like, globally in the industrialized world. So there's a good science to suggest that population control is a thing, and it's like going to be a thing going forward. We'll probably level off at something like 10 billion people. We're at 8 billion right now.
Just shy.
There are two schools of thoughts on what you can do as an individual. There are sort of the micro and the macro. There's one school of thought that says that individuals matter, and, like, you can change your light bulbs and drive an e-car and recycle and do all these things, and they will have a positive impact on your carbon footprint, and that's true. And then the macro view is that individuals don't matter, and this is an institutional problem, and we need to vote for people who will make institutional changes on a large scale. There are good arguments for both. Personally, I'm in the macro view. I don't think any individual matters for this problem, because you need to get the herd involved. Otherwise, what you're doing is, it's going to make you feel good, and there's something to that. But it's ultimately not going to make a big difference unless everybody's doing it at the same time. So personally, what I would say is go vote. If this is a priority for you, vote for the people that it's also a priority for. And hopefully, if people someday think on the institutional level that this is a problem worth fixing, we'll fix it. But yeah, that's sort of like the environmental political science cliff notes on how to think about this.
So I deal with this on a regular basis, and I have solar panels on my house. And when I taught a previous course, I showed my electric bill, and one of the students said, "Do you ever turn anything on?" We had a very low electric bill. So I've been pumping electricity back onto the grid for free, which drives me crazy. But I also think, just from a psychological point of view, I used to drive a car that had a 4-barrel carburetor and 8 cylinders and would get 8 miles to a gallon. So I agree that macro is far more important than micro, but just from a personal perspective, I'm doing it, right? I'm going to try. I have the solar panels. I'm installing air conditioning that is going to be driven completely off of the solar panels, not tapping into SDG&E at all. There's 2 reasons. I don't want to use the electricity generated from fossil fuels, and I don't want to give SDG&E any more money than I have to. So it is a very big issue, but I completely agree with you that voting for the right politicians, getting the right people in power that will invoke the right policies will help. I think macro-wise, it is working, right? So when you drive to Vegas, you can see the solar panel fields, right? I guess like, 20 minutes, a half hour outside of Vegas. So things are changing and moving in the right direction, and they have to continue.
Yeah, and I guess I should clarify a little bit here that from a macro perspective, sort of losing my train of thought. Crap.
That's okay. You're allowed to, because it makes me feel younger.
No, I got to say this. Oh, no. Oh, I had it.
From a macro. That's okay.
I can't remember. I'll email you with the response. I had a good thought about what you were saying, and then I completely lost it, but continue. Go ahead.
Cool. Well, we are now 5 minutes over, and it is a Friday. Dr. Amaya, again, I learn new things every time you give a presentation. And like I said, you should be teaching at a university you got to sneak in a class at some point. So you're really good. Thank you. We really appreciate your presentation. We think this is really important material. And I love that SUS effect. That is like really cool data. So
I remembered what I want to say now, and I got to say it now. The reason why I adhere to the macro effect is because of the time scale. So like individuals matter in the sense that like over a long period of time, if the herd gets together, it's going to make a difference. But I guess my point is that we need to make changes on such a time scale that we need institutional fixes like overnight, relatively speaking. That's sorry, I had to remember that. I was going to go crazy.
oh, I like that. I like that.